Hello, everyone. We will just give about 2 minutes for everyone, all the participants to come in before we start. Okay, I think this is 6:03, so I believe we can start right now. Good evening, everyone, and welcome to the OSPE Toronto Exchange virtual session. This is Net Zero Energy Building. My name is Bob Warren. I am a mechanical engineer by discipline, and most of my experience has been in the oil and gas sector. I will be your moderator for the event this evening. The OSPE Exchange Hubs is to expand its reach across Ontario by providing community gathering points for OSPE members to share, discuss, and contribute to OSPE initiatives and priorities, advocacy, professional development, and more. On behalf of all OSPE members, thank you to our partners for your incredible and ongoing support of Ontario's engineering community. In saying that, OSPE's Toronto Exchange Hub organized this event. The Net Zero Energy Building is one of the upcoming fronts to fight human-induced climate change and reduce GHG emission levels. Please note, this session will be recorded. I would also like to go over a few housekeeping rules for this Zoom event. All microphones will be on mute. So if you have any questions, you will not be able to ask them during the meeting, but please, you can type them in the chat box. An OSPE staff member will be monitoring, and the questions will be played out during the Q&A session of the event. Before we begin, we would like to take a moment to acknowledge that we are coming to you from Toronto, which is the dish with one spoon territory. We respectfully acknowledge the past and present traditional stewards of the land and their unique role in the life of the region. Toronto is on the traditional territory of the Anishinaabe, the Haudenosaunee, and the Wendat people, and is covered by Treaty 13 with the Mississaugas of the Credit First Nation. We pay our respects to the elders past, present, and emerging. As settlers, we are grateful for the opportunity to live, work, and play in this territory. Without further delay, we would like to begin the session. So I would hand over to Reza to begin the presentation. Thank you.
Thanks, Bob, for the introduction. Hi, everyone. Today, we will go through the review and a brief introduction for the net zero energy buildings. And just pop up my which monitor I have to use. Share my screen, and I believe I have to use this screen. Okay. Just I believe everybody can see it now. So I will start our presentation today, which is about net zero energy buildings, and I'm Reza Danesh, or by longer last name, Danesh Azarian. I'm a postdoctoral fellow at University of Toronto, Civil and Mineral Engineering Department. We spend the majority of our lives in buildings, so our houses, offices, and the community centers require heating, cooling, and lighting. In Canada, buildings produce 12% of our national emissions, mostly space and water heating. If you add the indirect emissions from using electricity, that share jumps to 17%. And again, it's just for the residential. And in making them more energy efficient, they represent a big economic opportunity. As you can see in here, we have a large portions of heating in our energy distribution for the residential sector. Considering water heating, space heating, and space cooling all together, they are accountable for 83% of the total energy used for residential buildings. So by coming to this point, we can see there's a big opportunity to consider net zero energy buildings. Let's see what's a net zero energy building. By considering the basic definition of a net zero energy building is that it's generate as much energy as it uses over the course of a year. This building is directly connected to the electric grid for balancing energy production and use annually. When the grid goes down, the building goes down as well, and it's pretty simple like this. But we have to consider the site boundaries for the energy transfer within the building, and we are going to keep it pretty simple. Let's see what's the site boundary we are talking about. The site boundary represents a meaningful boundary that is functionally part of the buildings. So for example, for a single building on a single property, the site boundary is just typically the property boundary, like just the lot we are talking about. The site boundary should include the point of the utility interface. So considering this figure, you can see the site boundary of energy and how it forms from building energy, on-site renewable energy production, delivered energy, and exported energy. In here, we have two types of lines. One of them are the dashed line. Let me just grab my laser pointer. Maybe it's going to. We have the dashed lines, and we have solid lines. The dashed lines represent the energy transfer within the boundary, which means they are on site. And the same thing as solar panels, we have some of our houses, they have actually, not all of us. But also we have some delivered energy from the grid. In the meantime, some of the buildings that are well prepared and they're functionally better than like a normal building, which they can export energy to the grid. And we are going to talk about in details about each part of these energy sections in details in next slides. But the basic needs we have to consider in a buildings are the meaningfully are heating, cooling, ventilation, door, and DHW. It's the direct water heating, lighting, and considering the plug loads and the process of the whole system. But in the definition, we have four main different net zero energy buildings. But again, it's in particular from one of the definitions like to be considered. Some textbooks or maybe some firms or some countries, they might have different definitions. And we are talking in particular to North American firms and companies for these definitions. The first one, which we are going to talk about, is the net zero energy by site. The second one is the net zero energy by source, and net zero energy by electric, considering the electricity, and the final one, which will be the net zero energy carbon. And in detail, we are going to talk about each of them, but I will mostly go through the net zero energy, the carbon part. But for the net zero energy site, this is just a classic definition of a net zero energy building, which is able to produce and utilize all the energy needed for a year on site. Traditionally, these buildings rely on the electric grid to balance energy needs as the storage provider, which means like during the day, they usually use they usually just store the energy and then they give it or export it to the grid. But during the night, they usually use it from the grid. So we are going to consider a balance in this area for these type of buildings to consider them net zero energy inside. But another part, it's the net zero energy by source. This definition looks to balance a building energy use and the energy losses of the energy grid providing it. And it's pretty rare to consider these type of net zero energy buildings. Different energy grids have published energy loss factors for using electricity and natural gas. By considering all of these losses, a building is accounting for its larger footprint and energy needs. This is a way to account for average grid carbon emissions today, since accounting of energy use at the building and upstream on the grid is the same as accounting for carbon emissions. This definition of a building may still use natural gas on site or other form of combustibles. The grid impact is lower for gas since it's converted at a building. Sharing operating costs between fuel types can be difficult, and often energy generation on site from the electricity cannot count towards equivalent natural gas cost benefits. And it's, as I mentioned, like it's pretty rare to consider this definition, but still we have this definition as a part of net zero energy buildings. The other one, which is much more familiar with people about net zero energy buildings, it's considering the electricity. But for this one, we are mostly talking about the commercial buildings, and they have called themselves net zero electric, which means all the electricity used on site is balanced with energy generation typically on site as well. Often buildings which still use natural gas for some heating or for some cooking opt for this definition as a way to deliver building efficiency and reduce energy costs. There is no official organization which provides a certification for this achievement. It's often used by private developers or large agencies with energy performance criteria for buildings. And when we are talking about net zero energy buildings, mainly we want to get the certification for a building to consider it's the same as like LEED, because like a building can be a LEED platinum or LEED gold, but it doesn't need to be exactly net zero energy. So these are both together to have a completely functional and efficient building. And the last one, which is net zero energy considering carbon and emissions. This type of zero energy buildings is defined as one of with net zero energy carbon, also known as zero emissions buildings. Typically, the energy used on site or off-site of a building is balanced with renewable energy on site. Only the energy use of the building only is considered, though this definition can be expanded to include emissions generated in the construction of the building or the embodied carbon of the building materials. So if I want to clarify this part, because we know like using the different materials, let's say wood or kind of like wood material in our building, we have to take care of the carbon footprint of those material as well. But the main thing in here, when we are talking about net zero energy carbon emission buildings, we don't account those values. But for sure in future, we have to step up and consider those values as well to have a net zero building. But there are several factors in designing an energy efficient building that achieve net zero energy goals. To construct a net zero energy building, you must take several conditions into consideration. The building site where you are building, the climate, and the building's exposure all have an effect, considering the wind patterns, temperature, or rain patterns. Because basically in some of the examples you are going to see, like in Canada, how they consider these parameters to have a completely large scale net zero carbon building. The other part, which is important also, it's the orientation of the building depends on this. It's important for a building to achieve net zero energy. Certain renewable energy generation mechanisms, like solar panels, work best when the building is facing south. But in the meantime, factors that conserve energy are also important. Because like considering harnessing the sun's energy, you can conserve by orienting your building to take maximum advantage of the shade as well. In warm climates, this means you'll need to use the air conditioning less to keep your building cool. Also, your utility bills as well to be down as well, so you can save so much more money in this site. Lighting is another important factor because the lighting almost takes 25% of our total energy consumption. So orienting your building to take advantage of natural lighting can reduce that load. So the arrangement and the use of skylights are the strategies which are important to achieve this point. Also, you can situate your building to take advantage of the natural breeze as well. So using natural sources to power your building's energy systems and reduce energy requirements will conserve resources at the same time. And considering the passive strategies, and we will go, so what are the passive strategies? One of the things to make our building a green building or net zero building is considering the design of it and the passive strategies to make it much more efficient. We have to make sure to select the best insulating materials possible so the building conserves as much as energy possible. Windows are another option. Usually, maybe 10 years ago, we were talking about dual pane panels. But these days, we are talking about triple pane panels, which are effectively sealed. They can pose a major factor in conserving energy. Passive strategies aren't about energy production. They're about minimizing the energy use and maximizing the energy performance. So we are trying to conserve energy by the passive strategies, and we are not talking about producing any energy in here. In fact, they operate without energy use, which is why they help buildings achieve net zero energy use. One of the things to consider at this point is the high efficiency appliances. They require less energy and lighten the overall energy bill. The same thing can happen by considering low energy HVAC systems. And also air sealing can prevent cooled or heated air from escaping through cracks, often around the openings such as windows and doors. And also another point which is important, it's the insulation, which performs the same function by providing an extra barrier between the interior and the exterior of a building. This layer traps heat in winter and cool air-conditioned air in summer that otherwise might escape through walls and ceiling. The effectiveness of insulations are related to the R values we usually see on the insulation materials. These vary basically on the thickness and density and type of the insulation. But the used ones are the fiberglass or the foam boards or blocks. Also, for a passive design, we have considered ventilation. It is importantly considering the climate, specifically in like tropical climates. So this ventilation part, it might not be that much important in Canada because like we have cold winters, but still we have to consider it a bit for the hot summers which we have in like areas like Toronto. It's necessary to replace a stale air with fresh air. This can help to moderate internal temperature while reducing the buildup of moisture that can cause mold and bad odors. The energy used to maintain proper ventilation by using electrical fans, for examples. And the other part can be considered as the architectural design, which new buildings maximizes the efficiency and promotes sustainability. But I have to mention, like all of these parts which we talked about, they're not just alone by themselves. They're kind of a package we have to consider all together. Also, when we are considering all together, there's an important point in here, which are us, the occupants in the buildings. So there are several standards they have to be considered. You might know ASHRAE, or it's the abbreviation for the American Society of Heating, Refrigeration, and Air Conditioning Engineers. And they created standards which founded from 1894, and they have 87 active standards and guidelines for the occupants of buildings. So in these 87 standards, we have to consider thermal comfort of the occupant, the energy conservation in buildings, reduction of refrigerant emissions. Maybe you heard of like maybe like it was 20 years ago, we were talking about the ozone layer and the CFCs. The same thing in here, like it's the reduction of refrigerant emissions. And the most important part of the work is the indoor air quality, which is related to the ventilation to have fresh air in our buildings. And the final step in designing high performance buildings is considering the renewable energy sources based on the buildings. If the building is industrial scale, we can consider even wind generators or the wind turbines, and they can be used even on site rather than off site. So like in some Scandinavian countries like Denmark, we have off-site wind generators because they don't have that enough land to have it. Also, for the wind turbines or generators, we have to consider a place which is efficient because they're pretty expensive. But when they are in a good place, they are their performance are good and we can consider it. And considering the renewable energies is part of active strategies, which means like reduce energy consumption during the building process through the use of renewable energy strategies. So the most familiar with for everyone is the PV panels or photovoltaic panels. They are just a direct conversion of light in electric power using semiconducting materials such as silicon. And those black plates you usually see, those are silicons. Each solar panel contains numerous photovoltaic cells, which work together to produce electricity. Another part is the wind power, and as we mentioned, it's pretty important in industrial sections where we have enough land to consider the wind turbines. But for the buildings, the other thing we can consider is the geothermal power. Geothermal power involves water pressure in the form of steam. For this kind of part, we have to consider wells to be drilled, which they can be 50, 100 feet or to 1,000 feet underground. And we usually have heat pumps to pump this heat to the building. And then the pressure drops and the water turns to the steam by considering the whole system. And the steam spins a turbine connected to a generator so we can have electricity. And on the other side, we can use it as a part of heating system for the building. So in here, like for geothermal, like in this picture, you can see it's a horizontal one. So for this one, we don't need to dig that much deep, and it can be just pretty flat place, but it has to be under the frost line. Because like in Canada, in different regions, the frost line for soil it's different. As I remember, for Toronto, we are talking about like depths of 8 meters, if I'm not wrong, because I worked on a project. So we had to consider like 8 meters down the surface. So there we have a stable temperature of 8 to 10 degrees C, which can be used as a generator, heat generator for us. The other part which can be considered for different buildings, basically for residential, it can be considered as well, is the solar thermal power systems. In some type, we use mirrors to collect sunlight and concentrate it. This part is difficult, perfectly effective, and we have different solar farms like in California. Then they call it heliostat farms. They usually raises the temperature until it's high enough to produce electricity. It's the same thing as combustibles, but instead of producing carbon, we are using just a clean source of energy to boil up the water we need. And another thing we can consider, which is again in California, and I believe in California again, it's the parabolic trough collectors. They don't need anything to perform. They're just kind of half a cylinder, and there's a tube in the middle of their focal line, so they can be used. And even these ones, the part like the good parabolic trough collectors, they can reach up even to 500 degrees C, so which is a high temperature for a building. But there is something we have to consider. Like, okay, if we are constructing a building or we are having a building from scratch, so we can consider those things together. But simply, we cannot say, okay, let's demolish our place and build from scratch. But we have to retrofit different buildings. Simply retrofitting your buildings won't automatically create net zero energy savings. Slight changes might not be enough. Just by adding solar panel, it doesn't mean like you have a net zero energy building. Furthermore, every case is different, so we cannot have one size fits all approach to retrofitting. The amount of work depends on how extensive the modifications needs to be, and that factors all the climate, the building's original design, its structural stability, and material use. These all together affect the cost of the project, which is the important point for the project. Although retrofitting is almost always less expensive than starting from scratch, and we can consider also the tax incentives and other stimulus which can offset the long-term costs. And doing a good retrofitting, actually, you can sell your energy. And in different countries, I know the amount per kilowatt hour, the like the price is different. But to retrofit a building, we have to consider 5 important points. We have to replace outdated mechanical systems, and we have to consider insulate leaks and replace old windows, purchase Energy Star's products, and switch to renewable energy. And in detail, we are going to talk about each one of them. The first one, replacing the outdated mechanical systems. It's pretty straightforward. Trade out the furnace or boiler or window air conditioner for a central system or solar water heating. Insulate the leaks the same. You have to consider insulating your basement to reduce the mold, insulate roofs and foundations with spray foam to keep building interiors cool in the summer and warm in the winter, and insulate empty walls to effectively warm an older house. So the dry walls, usually they have to be filled in. And also the other thing you have to consider is replacing your old windows. Windows are similar to insulation. They prevent climate controlled air from escaping while keeping air and water from getting into the house. Triple pane glass windows are the best option for maximum energy efficiency, while we can consider the dual pane design. And the triple pane, but it's more efficient in this case. Windows should be installed properly to prevent water damage or air infiltration for optimal energy efficiency. Also, the placement of windows are important. For example, windows placed on east or west walls can waste twice as much energy as those facing north or south. This is because they face direct sunlight in the mornings and afternoons, respectively. And also, we have to consider low emissivity glass coatings, which they can reduce the amount of infrared and UV light that passes through the glass. But we have to consider these coatings, they don't affect the amount of visible light that comes through. So by doing these coatings, we can keep our interior cool by reflecting the heat in summer, retain warmth by reflecting cold air during the cold winters, and prevent fade damage by blocking UV rays. The next one we have to consider is just purchasing Energy Star products. When we are usually talking about energy products, we think we are talking about refrigerators, washers, and dryers. But actually, furnaces, we have the Energy Star products for furnace, for central or room air conditioners, even for air source heat pumps, ground source heat pumps. Also, another thing we can consider, the Energy Star also certifies building products, including roofing products, ceiling and insulations, storm windows and residential windows, doors, and skylights. They might be a bit higher and a bit pricey, but it's good in a long run, considering the bills. And the other thing, if the budget can help us, it's a retrofit of produce your own energy using various types of renewable energy sources. to help and conserve energy. As we talked about it, the wind power, it's not feasible for a building if it's a residential. But if it can be offsite, it can be a help for the electricity, like for the grid, so it can be used for the residential buildings and the condominiums or apartments. So it can be again a help. Again, the same as hydroelectric, because like for the buildings, we cannot have a hydroelectric dam. But for a city, yes, we can have. So it can be a bigger picture to follow for a renewable energy saving. But we have to consider there are several barriers in Canada. One of them is the knowledge barrier, refers to both knowledge deficiency about the science and technology of the net zero energy homes and knowledge inadequacy about how to use them. A net zero energy home has the potential to reduce energy while adding the security to the energy supply, both of which can be a relative advantage when compared to conventional houses. However, we have to consider the upfront technology cost remains a barrier. So usually homebuyers they tend to justify their purchases based on their immediate visible costs and investments, and not the potential future benefits arising from energy efficiency or lower long-term environmental harm. And the other thing we have to consider is the economic feasibility of purchasing a net zero energy home, which remains a barrier to its adoption. Conventional houses construction firms are not interested in zero carbon buildings due to steep construction costs, limited access to construction funding for these kinds of projects, and the high demand uncertainty in the market. So that's the reason we cannot see that much of net zero energy buildings these days. But considering a model for addressing all of the barriers that affect the willingness of consumers to adapt net zero energy housing can be seen in here. We have the social acceptance attributes and the economic feasibility attributes, which the complexity, the ease of use, like relative advantage and disadvantages, like the extra cost when compared to a conventional or typical home. So these are the whole thing they have to be considered all together. But in the meantime, we have to educate people that we are going to need these buildings for our green future. But let's talk about like bigger plans. Like large, for example, like in Maryland, we have the largest net zero energy building in the world. It's a huge building which is spread across an area of 135,000 square feet, and it's called Unisphere. It's in the middle of the city, in downtown of Silver Spring, and it has all the technologies we are thinking of. And it's a complete net zero energy construction. It's completed in 2018, and it's it's now the world's largest office building that works on the concept of zero energy, and it's actually working now. It's not just on paper. The Unisphere combines automations like solar PV systems, geothermal wells, high-performance electromagnetic envelopes, Earth-coupled heating cooling system, a thermal pool. All together, they help the building function with no carbon footprint. This building sells more than it buys from the grid. So in particular, it has 3,000 solar panels and 1,000, so they have the extra space for 1,000. And that 1,000, actually, they are selling the electricity from this 1,000 solar panels to the government. So actually, they are producing somehow kind of like pay. This is kind of a payback for the investment. The Unisphere, as I mentioned, it has 3,000 high efficiency solar panels. There are fourth generation of solar panels, which they're expensive now, but in the meantime, when we are talking about the solar panels, we are talking about like every 5 year a new generation comes to the market. So it is going to be cheaper and cheaper in the future years. And the whole photovoltaic system is designed to produce over 1 megawatt of power for this building. Also, it has 52 geothermal wells drilled more than 500 feet into the ground, which they can be used to increase the efficiency of the heating and cooling system between 25 to 50%. This system cycles the hot or cold water depending on the season, because ground is a constant temperature, so it can be used as a heat source or a heat sink during different seasons. And the building, like in here, you can see like if we are talking about winter, so we have 8 to 10 degrees C heat source in here. We can heat up our water and our space. And during the summer, it can be the vice versa. We can cool down our places. But also one thing in here I wanted to show, it's the thermal pool. It's a really beautiful because the thing in here they considered it's almost too old. It's we are talking about like this kind of conception comes from a traditional homes in Middle East, mostly in Iran, Yazd part. It's a city. It's a completely hot place, but they can cool down their places without having kind of like air conditioning systems. So in conjunction with the geothermal well system, the thermal pool will also help the building efficiency by lessening the load of the HVAC system, which is located in the building atrium. The thermal pool will also serve as a source of evaporative cooling and heat rejection. And let's come to Canada and talk about our buildings. The very first building in Canada to be certified as a zero carbon building under Canadian Green Building Council is Evolve 1 urban office buildings in Waterloo, Ontario. The building also achieved the permanent status of being LEED Platinum certified as well. They use this solar wall for air heating, and they include the key on-site renewable energy technologies, which was blended with the building. So in particular for this building, which we are talking about 110,000 square feet of facility, and it's one of the most beautiful and uniquely modern multi-tenant office buildings in Canada. This building is owned by Cora Group and designed by Stantec. It will set the standards for future buildings as it's the first building to be considered net zero energy. And actually, it's a positive energy where it's achieved on-site renewable energy production to provide 105% of the required energy for this building. One of the things like for this building is the solar wall, as I mentioned, and it's a pretty big wall where we are talking about on the previous slide I showed. It's like 500 square meter of gray color solar wall panels were integrated to the south wall. As we mentioned, the south wall are the best for energy part, solar energy part. But in a typical zero carbon building, we can see these systems all together working each other, like considering the solar heating wall, cistern water, geothermal open panel, variable refrigerant system, which has its VRF, or solar thermal systems, hot water heaters and boilers, and so on. And it's pretty big where we are considering this. But the main thing I want to show, as a kind of, I have to say, the diamond of green buildings or energy efficient buildings in Ontario as an institutional place. So you might know the shape, and it's the Mohawk College. It's the Hamilton facility, which is one of the region's first net zero energy institutional buildings when it opens its doors to these students. As the largest zero institutional building in Canada, the Joyce Center is a living lab for a student, offering them hands-on access to monitoring and operation of zero carbon building certified system. Basically, for this building, they're projected to consider like 50 millions, like the projected values as this. But actually, when they come up with the final values, they were much more less than the projected values. And you can see the building size was much more higher. Also, for the zero carbon system of this building, they considered the heat pumps, geothermal field, and also dedicated air system, solar thermal for preheating domestic heat water, and the heat pumps for an auxiliary system of directly heat water system. It's the same as the previous one, as we mentioned in Unisphere. They considered different large drilled wells for the geothermal system. They considered a gigantic HORV system to make it much more efficient for a building. And also they put 1,980 solar panels on the total area, where they have also a backup plan for if there's going to be a failure in the system, this backup plan can help the system as well. This is the whole thing you can see as a solar panels, and here it's a beautiful building, to be honest. If you are living in Toronto, to be honest, I would suggest to go and visit this place as a design of it. And also considering the solar thermal system of this building, it's considered for simply just domestic heat water, and they augmented condenser water loop heating. And they consider Wiseman panels and tanks and controls for this system. And in the while, also they consider the rainwater reservoir. And it's one of the novelties for this building, because most of the buildings, they don't consider this part. And the last part I would like to mention, it's the study period for this building, where was actually before the pandemic. The top floor of this building wasn't fully occupied. But actually, when they go throughout this study, they see everything was normal, where the PV production was 6% less than what was nominal, and the building consumption was 20% less than what they expected. So I believe maybe I might go over 40 minutes like I had to talk. I believe I can stop it here, because it's just for the energy calculations, and I can share it later if we have time, but maybe after the questions I can just share this part.
Okay, thank you, Reza, for the wonderful presentation. Yeah, the next part will be the Q&A session. Right now, I do not see some questions, but we do have some questions that we had aside for this event. One of them has to do with investing in the net zero energy buildings. You talked about retrofit. What are the advantages for an old building? I'm talking about the cost benefits of putting that. Does it make economic sense to do that retrofit to net zero?
Um, Again, if you're talking about the long term, yes. But the main thing we have to consider for the retrofit, it's the incentives by the governments. Because some of the governments, like in Europe, they're not willing to buy like the electricity produced by private places. But in Canada, it's the vice versa, and that's good actually. But the things like the rates are different from one province to the other one. So
Okay.
it's kind of like we cannot say like we can just um, consider just one approach for all buildings. But yes, in sometimes it needs just a retrofit, but sometimes unfortunately it doesn't make sense and it must be demolished and go from scratch to make it uh, cost effective.
Okay. All right. Thank you. I have another question from Said. It says, to what extent does active system contribute to a net zero building in Canada? And how big a size of a building have you come across that has the net zero I mean, that's involved, I mean, due to heating, a net zero building, net zero energy building?
Actually, as a part of like my background is mechanical engineering, and I'm working also as a consultant. So considering those talking about like the active energy, we are considering like in Canada, we are mostly considering geothermal systems or the ground source heat pumps. Actually, I was involved in two different projects where we were talking about multi-unit residential buildings in Ottawa and in Toronto, where there are like they're not skyscrapers, but they were like 35 floors, and we are talking about 500, as I believe, 550 units. And we were able, by considering geothermal system just for this ground source heat pump system for these buildings, to make them net zero emission. So it's kind of another definition. But the thing, as said, as like it was a big project because we considered like around 200 boreholes or geothermal wells to be drilled for this particular project in Ottawa. So this is actually a great investment, but uh, basically it was the ground source heat pump was able to produce 100% of the needed heating system, like the for heating up the spaces, for warming up or heating up the water. But again, it's in particular, but for North America, we can say for Canada, ground source heat pumps are the main active renewable energy part.
Okay. I think we can just have this as a last question coming from Said as well. Now he's saying that fine, this works well, but once you go over 3-4 floors in the building, I mean, yeah, how is the efficiency like, and what's the way forward on that? Does it still remain that efficient, or I mean, is there something extra that can be done?
Actually, for like 3, 4 floors, we are talking about like small residential buildings actually. In those points, we don't need to consider, like again, for the solar panels, yes, we can use it. There is no that much of like construction or drilling or installment costs for it, because they are just the panels, we can put them together. But for these buildings, if you want to consider geothermal systems, they don't need to be drilled vertically. For those ones, because like when we are talking about like 3 floors, 4 floors, they have a yard, which is kind of enough space to have a horizontal, which is kind of like the use site as a flat space, and we can use it as a ground source pump again. Again, we have another some in different works. We did some retrofitting for some schools. Actually, they had a great space for this ground source heat pump, where we were able to consider just the horizontal uh, connections for the geothermal system. But again, we are talking generally, not specifically, and but the whole thing I can say, yes, it's effective even for a small building.
Okay. Okay. All right. So I think this is as much of the questions we can take. If we have any more questions, we can just email them directly, and we'll be able to get the appropriate responses back to the participants. Okay. So this concludes our event. I would like to thank Riza, Daniel Shazarian, and the audience who took the time to attend this session. It was very informative, and I think there will be a follow-up email to the guests with more information on this conference. So thank you very much, everyone, and you do have a wonderful evening.